Hello everyone, in this video I'll be talking about MATLAB script on Upwind scheme to solve first order differential equations for advection equation where we have a first order derivative in time and first derivative in space. So to refresh our mind, the equation we're looking at is du dt plus v du dx equals 0, or basically what we call the advection equation. You can find that equation in the notes on page basically 166. So the equation we're looking at is the advection equation. We want to solve this using forward in time and backward or forward in space. So we have to see which one we have to use. The method is called Upwind, and there's a reason for it. We get to that in a minute. But basically, if we discretize our differential equation using forward in time, so this is forward in time where n is the index for the time, and that is equal to the negative v times derivative with respect to x. Now, the upper equation here, this one is backward in space, because we're looking at j minus 1, where j is the index for the x or for the spatial coordinates. This is forward in a space because it's j plus 1 minus j. The question is where we should use backward in space, where we should use forward in space for advection equation. And if you notice, for these two, we always use forward in time because that's n plus 1 minus n. We only have an option to either switch to backward in space or forward in space. So the idea is, basically, you can see that from the graph that we had last time. So if the velocity is positive, that means the information or the wave is coming from left to right. You can think of a flow in a channel. So if the velocity is positive, then the flow field or fluid is coming from left to right. If the fluid is coming from left to right, then you need to use backward difference, because for every point you know the flow field or the velocity or the concentration on the point behind you, because velocity is coming from left to right. So if you're sitting on any point in x or in spatial coordinate x, then the point behind you, which is x minus 1 or xi minus 1, then you know the information from there, because velocity is coming from left to right. So if you're sitting on any point, the velocity has gone past any point behind you. So you have to know the concentration of those points, or maybe you must have known those velocities or those concentrations. On the other side, if the velocity is negative, that means the flow or the velocity is from right to left, then at any given point, let's say I'm sitting at point xj, then you know, if you're sitting at point xj, then you know the concentration at j plus 1, because velocity is coming from right to left. So if I'm sitting here, you better use forward difference, because you're using information at point j plus 1 and j to calculate the derivatives, and you know the concentration at j plus 1 because velocity is coming from right to left. And once the wave or the information reaches at point j, that means it's already past j plus 1 point, because again the velocity is coming from right to left. So upshot is, when the velocity is positive, which means left to right, then you use backward difference space. You write j minus 1 for the spatial coordinate, for the spatial derivatives. And when the velocity is negative, which means the fluid is coming from right to left, then you should use forward in space. That means uj plus 1 minus uj. So this is called upwind. That means you have to see where the wind is coming from. If you're sitting at point j and the wind is coming from left, then you have to use upstream information, which means you have to use the concentration at j minus 1. If the wind is coming from right to left, and you're sitting at point J, then you have to use the concentration or the information at point J plus 1 and J to calculate the derivative at point J. You cannot use J minus 1 when the wind is coming from right to left, because if you're sitting at point J, information hasn't reached J minus 1, you don't have any information on that point yet. Okay, so now we put all of these into the MATLAB script. This is the MATLAB script for Upwind explicit method. Explicit because we're using explicit discretization for the spatial coordinates, not for time. So usually when we use explicit methods, that refers to the spatial coordinate. All right, so we're gonna start with clearing the screen, close all the current figures. Number of points, I put like 400 points across the x-axis and 100 points along the time axis. Remember, we have two independent variables, x and time, or x and t. Initial time 0, final time is 4. In the x domain, I put my left x, or the lower bound at -10 and upper bound at +10. Velocity is negative, is -1. That means the wind or the flow is coming from left to right. I'm sorry, from right to left. All right, so skip 5. This is just to make movie or animation, so you can just skip that for now. I create a time vector from t initial to t final with number of time points that we had here, about 100. So using the t vector, you can calculate dt, which is the difference between two successive time points. You do the same thing for x values. You discretize from minimum x to maximum x with the number of x points, and then you find the interval in x by the difference between two successive x points. Using the x and t vector, I create a mesh or a grid. So this grid has x-axis on the horizontal axis and time axis on the vertical. All right, so now I have a grid of x and time on a mesh. All right, so we create a matrix called U, or you can call it concentration matrix or the velocity matrix. So this matrix has the number of points equal to the number of x values, number of columns equal to the number of x values, and then number of rows equal to the number of t elements. All right, so we create our alpha, which, if you remember from CFL condition, that is the velocity times dt over dx. This is non-dimensionalized velocity. V is the real velocity, and then dx dt is, or dt dx is the reciprocal, the numerical velocity. And so what we are doing here is we're multiplying the actual velocity by, or divide by, the numerical velocity. So we know from CFL condition, if this is less than 1, then the method is converging. If it's bigger than 1, then it's diverging. So we have to actually make, this is a constraint on how small delta t and delta x can be. Okay, so we start by creating an initial concentration distribution. I used here a half cosine function. So I have a cosine squared, I have a cosine squared, and then I actually cut that beyond plus minus pi over 2. So that's basically half a cosine wave. I create that as an initial distribution. Then we check, so we go over basically the time points, and we check if alpha is negative, which means velocity is coming from right to left. Alpha negative means, remember from here, means velocity is negative. Velocity negative means it's the wind or the velocity is coming from right to left, and I have to use forward in a space, and that is forward in a space. So if you look at the I index, the second index is the index for x, so it's I plus 1 minus I, and then the time index is actually IT minus 1, so I moved actually IT from left to right, that's why it's plus here. But basically that's it minus 1 divided by del t. When you multiply by del t, you get alpha here. There's negative alpha because in the original advection equation we have du dt plus v du dx equals 0. And then once you move the v times du dx on the right side, you get actually minus sign here. Now on the other side, if alpha is positive, that means wind is coming from left to right, then you have to use backward difference in the space, and that's why we have I minus 1 on the right side. Alright, so by this time, or by this point, we calculate all of the velocities at different time. We iterate over a time cycle here. At every time cycle, we use information on at the previous time points, because I have t minus 1 on the right side, so I know everything at t minus 1. You see t minus 1, t minus 1, t minus 1. So using a t minus 1 information, you can find the information at any time t. Then we plot, and the way we plot, we use the x grid, and for every time point, you have the values from UMAT, which is the concentration. So you can now we can plot concentration against time and space using the mesh grid. This part is for animation. If you really want to see how the progression, or how the initial concentration diffuses, or advected over the spatial coordinate, then you can use this animated module. So the way to do that is you plot your concentration against x at every time. Then you give about 0.04 second pause, and then you're going to remove this plot, and then you basically plot the next distribution, or the distribution of the concentration at the next time point. So basically we're going to plot, we're going to wait for about fraction of a second, then we're going to remove that plot and plot the distribution at the next time point. If you do this fast, which is about 0.4 second interval between two frames, then a normal eye would see this as an animation. Alright, so let's get to the execution. So I'm going to run this as script and explain to you what's happening here. So initially I create a half sine wave, and we know that the velocity is negative because I put alpha or v equal -1. So initial concentration is like a bell shape, and it's going to move from right to left because the flow is coming from right to left. You see this as animation because basically I'm plotting very fast every frame in a fraction of a second, and that's why if you do that very quickly, you would see this as a movie. Vertical axis is the concentration, and horizontal axis is the x point. And I'm here showing how time is increasing. Alright, so that was about Upwind scheme for explicit discretization in space and time. In the next video, I'm going to show you how to do this for implicit discretization of x, or implicit discretization of advection equation. And then we're going to see how we can use Upwind scheme again. Now the second plot I have here is basically the steel frames. So if you extract the frames out of the animation and plot all of them on this graph, then you would see that this is basically the x, this is the time. You see a very fine mesh here. This is the mesh grid we created. At every time that you go across the time axis, you have the distribution, and you see that the distribution actually moves from left to right. If I actually rotate this, you would see this clearly. So here it is. You see that the wave is going from left to right. I'm sorry, from right to left. This is the x-axis, that's the time axis. So as we go over time, the wave actually goes from the positive x to the negative x. And so the magnitude-wise, we don't see a big of a change. Although we see some decay. You see that initially we start from this peak and now ended up having a bit lower peak. So we're going to talk about what's going on here, why the peak is shrinking. Alright, so hope this has been useful, and stay tuned for the next part of this video. Thanks a lot for watching.